let's look at some of the ways we can use Euler's formula. Obviously exponential functions. Seeing Euler's formula involves e to the power of something. We saw that e to the iota theta was cos theta plus I sine theta. However, because cosine is a periodic function, it must also be true then that e to the iota theta plus 2i k pi will be cos theta plus 2 pi k plus I sine theta plus 2 pi k, but that would be the same as cos theta plus I sine theta, because of multiples of 2 pi, assuming of course k is an integer. Well then really it's just the same as e to the iota theta itself. So what we're saying is our exponential function, when we're talking about this, is also a periodic function, period of 2 pi I. Trig functions, again there has to be a huge connection with trig functions because of the other part of Euler's formula, the cos theta plus I sine theta. Now we proved these two identities before. Z to the power of n plus 1 on Z to the power of n, or if you prefer Z to the power of n plus the conjugate of Z to the power of n if the modulus was 1, was equal to 2 cos n theta, and the corresponding one, Z to the power of n minus 1 on Z to the power of n is 2i sine n theta. So those are identities we had before. Well, if I rearrange those, I now come up with this expression. The cos of n theta would be a half of e to the n theta iota plus e to the minus n theta iota. I kind of used that yesterday. It's just that n was 1 if you remember, and in the example that we did I had e to the iota theta plus e to the minus iota theta, and the 2 was on the other side. It was equal to 2 cos theta. We used that idea, basically saying when you add conjugates together you get twice the real part. And the corresponding one for sine would look something like that. But of course with the sine, we're dealing with the imaginary parts, so we don't get a half out the front there, we get 1 on 2i. So let's prove some more trig identities then. The one we started with, sine squared plus cos squared is equal to 1. So now here's another way of proving that identity. If I now substitute in these relationships for sine and cos, and in this case n's just 1. Wow, let's expand this all out. We have a common factor of a quarter. Expanding out, we get that expression there. There's a lot of cancelling that will happen. In fact, the parentheses just comes out to be 4. Quarter of 4 is 1. We've proved our identity. How about this one? We saw this the other day. We ended up with sine cubed, or was it cos cubed we did? But anyway, we saw something like this. Sine cubed theta was equal to 3/4 sine theta minus 1/4 sine 3 theta. Alright, well sine cubed theta, if I substitute in that relationship for sine, expand it out, it's a cubic. Let's play around with this. Now I want to group the ones where the powers are the same or the conjugate, and so I'll get 3 of e to the iota theta minus e to the minus iota theta, and then minus grouping the ones that have the power of 3 iota theta and its conjugate there, which then allows me to substitute back in for sine theta and sine 3 theta, and we get our relationship. How about this one? Our product to sum relationship there. Okay. Again, let's substitute in the results that we had with the exponentials. Playing with the top of the fraction, we end up with this result. But again, let's group them with the power and its conjugate. And I'll separate them into 2 fractions to make it a little bit easier. They're both over 2i, of course. And we end up with sine of alpha plus beta plus sine of alpha minus beta. Finding roots of complex numbers. Well, we've seen a couple of ways of doing this already. Here's yet another way. Find the square root of 1 minus root 3i. So z squared, if I put it in exponential form, will become 2e to the minus I pi on 3. So z then will be the square root of 2, but then we'd have half of this argument. So minus I pi on 6, but we want 2 solutions. So it'll be plus pi k. Well, why pi k? Well, because really what we're saying is e to the z plus 2i pi k, but we're halving the argument, so it becomes pi k there. And k is equal to 0 and 1. And so we get minus I pi on 6 and 5 I pi on 6, and I just noticed that probably should be grouped, shouldn't it? Because the I is with the pi k as well. So that should be grouped together. And if I want to actually calculate it out, I can put it back into, well, the mod arg form, then calculate what that is, and we get the 2 square roots. So how many ways have we got of finding square roots now? Is that about the 4th way of doing it? Let's look at some HSC ones then. The very first paper in the new course was the 2020 paper, question 9, which means it was actually one of the multiple choice questions. But it asked, what is the maximum value of this expression? Well, if I let z equal e to the iota theta, now the modulus of z would be 1, because coefficient of e to the iota theta in this case is 1. So we know that. Therefore, I know that all the solutions will lie on this circle. All the possible z's lie on that circle. Now what is the modulus of z minus 2? Well, we know it's the length of the vector that would join any of those z's to the point 2. So I'll just pick one there. So that could be an example of one. And what is the modulus of z plus 2? It would be the length of the vector when I join any of those z's up to minus 2. But because I've already drawn the first one in, it's going to be the same z. So let's draw that one in. We want to know when are the sum of those two distances at a maximum. And actually I deliberately put it at the point where it would be a maximum. It's going to be a maximum there. And at that point we will get, well, let's work out the length. I've got a right angled triangle here. I can work out the length is root 5. The other one by symmetry must also be root 5. Therefore that maximum distance is 2 root 5. So that's a nice geometrical way of solving that problem. The following year, now we're getting into the back half of the paper. Remember there's 16 questions all up. The last 3 are when it starts becoming interesting. So 14C part 2. It said by using part I, well, I won't worry about doing part I. What they asked you to do in part I was to prove this relationship. That cos of 5 theta was equal to 16 cos to the power of 5 theta minus 20 cos cubed plus 5 cos. Alright, so it's using that or otherwise. We're going to show that the real part of e to the power of I pi on 10 is the square root of 5 plus the square root of 5 over 8. Well, what is the real part of that? Well, the real part would be the cosine of the argument, so the cosine of pi on 10. So I'll let theta equal pi on 10. It said use part I, I'll substitute it into that result. And when I substitute it into that result, lovely, the cos 5 theta becomes the cos of pi on 2, which I know is 0. Okay, well if I now say x is cos pi on 2, I mean it's a subtle difference, I could have made theta as well, but let's say it's x, just to make it look more like a polynomial. We've got this polynomial equation to solve, but what we're essentially saying is the solution to this, well one of the solutions, there'll be 5, one of those 5 solutions will be the cosine of pi on 10, and the cosine of pi on 10 is the real part that I'm looking for. So I need to solve this and work out which one of the 5 solutions is the one I'm looking for. Well, straight away I'm going to divide everything by x, because clearly x is not 0. I know the cos of pi on 10 is not 0. So I can divide by that. I'm not dividing by 0. That's fine. It gives me a little bit easier equation to solve. I've now got a quartic to solve rather than a pentic, but nicely this quartic's in the form of a quadratic. I'll use the quadratic formula then. So x squared would end up being 20 plus or minus the square root of 320 over 32, which simplifies down. That's x squared. Therefore, I'm making the statement that x would be the square root of that. I didn't worry about the negative square root because I know pi on 10 is an acute angle, so I know it has to be the positive square root. So I've got rid of half of them already. Now which one of these 2? So alright, I can get rid of the negative ones. I've still got 2 to decide upon. It's either going to be 0.59 or 0.95. Nice symmetry there. Which one? If I look at the cosine graph then, and just have a look at some things I know. I know, for instance, the cos of pi on 4. It's one of our exact values. It's 1 on root 2, which is, well, to 2 decimal places is 0.71. I also know pi on 10 is smaller than pi on 4. the answer would actually be the larger of the two, because looking at the graph it's going to be above that y value. So I'm looking for the 0.95, which was the one that was the square root of 5 plus the square root of 5 on 8. That saved me finding all the other solutions to narrow down, or which one would it be. Just look at the graph and then we can get it. That, of course, wasn't the question that was asked of me. The question that was asked of me was the real part, so concluded with what they were looking for. The real part of e to the I pi on 10 would be the square root of 5 plus the square root of 5 over 8. Let's have a look at this one from last year's. Z's the complex number. Z is e to the power of I pi on 6. W is the other complex number there, e to the 3 I pi on 4, which is nice. Both of them have got exact values that we can find in the arguments. We can find those if we have to. Well, it looks like we do have to, because they've given us the hint by writing Z and W in Cartesian form. So I'll convert from exponential to mod arg, which then allows me to find Cartesian. We get root 3 on 2 plus a half I for Z, and W we get minus 1 on root 2 plus 1 on root 2I. So we've got Z and W, or otherwise, well, why go otherwise? They've given us the hint. Now we've got to come up with that expression, the modulus. Well, okay, let's substitute in what we just found. We're finding the modulus of this, okay, well, it's going to be the real part squared plus the imaginary part squared. Expand that all out, tidy it up. Actually, there's still some cancelling there that can happen. Yes, 2 goes in everything. There's what we were looking for. So 4 minus root 6 plus root 2 over 2. Okay, so that was the first part. ZW and the complex number Z plus W are represented in the complex plane with vectors. Show that angle AOC is 7 pi on 24. Well, I need to draw a diagram here to get my head around what they're doing. Z is over there. W would be in the second quadrant. I know the length of those vectors will be the same because the modulus of both of those was 1. So they were both in length 1. So I know they're the same. The third vector, Z plus W, would be the diagonal of that, well, I was going to say parallelogram, but it's a rhombus, isn't it? Because we've got the adjacent sides being equal. So I know the third vector we're talking about is that diagonal there. We want to find angle AOC. Well, I can easily find angle AOB. That's going to be the argument of W minus the argument of Z. A little bit of calculation. 7 pi on 12. That feels nice because look, we're heading towards, it's got a 7 pi on the top. But hang on a sec. Angle AOC. Well, the diagonal in a rhombus, I know, bisects that vertex. So it's got to be half of what I just found. There's my 7 pi on 24 that I'm looking for. From there, whoa, deduce that the cosine of 7 pi on 24 is this lovely expression. Well, the square root of 8 minus 2 root 6 plus 2 root 2 all over 4. Well, I've now got a triangle. I know an angle. Let's use our cosine rule. We got the length of 3 sides. We're trying to, we've got an angle. Actually, we've got everything. We've got the 3 sides and we've got the angle. So we can find what we want. I can certainly tidy up that fraction from the cosine rule, because remember we said the modulus of Z and the modulus of W, they were both equal to 1. So on the top I've got 1 minus 1, that goes away. On the bottom, that mod Z is just 1, but I'm multiplying, it goes away. Now I've got the modulus of Z plus W squared on the modulus of Z plus W. So it's a half of the modulus of Z plus W, but that of course is what we found in the previous part. So it's a half of that. We have our result. They wanted us to find that. All right, another one from last year's. 16, so the very last question, but the first part of the last question. As soon as I see something like that, now, even before they've told me part I, the first thing I think of when I see that is, roots of unity. Because I see that 2 pi on 3, and I know that is one of the cube roots of unity. And indeed, look at what they're asking us to show. 1 plus w squared equals 0. However, they haven't actually told me that's a root of unity. So I can't just say, oh, because it's a cube root of unity, therefore 1 plus w squared is equal to 0, which we know is a relationship for that. So we've got to do it another way. I guess let's just substitute in and show that that's equal to 0. So if I substitute in, this is what I get. But of course, I could rewrite 4i pi on 3 as minus 2i pi on 3. Now from this point I've got a couple of options, because at this point I now can see it and go, oh look, well I know they're conjugates, so I could say it's twice the real part and go from there. Or I could simply expand the whole thing out and then it becomes obvious that they're conjugates, because look what we've got. I sine 2 pi on 3, and over here I've got I sine minus 2 pi on 3. However we do it, we end up with 0 eventually. Okay, we got the first bit. Then it became very interesting. The vertices of a triangle can be labelled A, B and C, but you can do it in one of two ways. You could label it anti-clockwise or you could label it clockwise. Three complex numbers, A, B and C, are represented in that plane by the points A, B and C. We're looking at the first case, when it's anti-clockwise and it's an equilateral triangle. Then this relationship should hold. A plus BW plus CW squared is equal to 0. So there's my triangle. How am I going to do this? Well, what I'm going to do is I'm going to translate this vector up here joining C. Now what can I say? Well, remember it's an equilateral triangle, so all these things are equal. Because I've translated that vector up, it's going to be equal as well. That angle there must be 2 pi on 3. A little bit of geometry there. This was an equilateral triangle. So if that angle is pi on 3, co-interior angles got to add up to 180 or pi. Therefore that angle's 2 pi on 3. Now, I could find an expression for AB, which would be the cis of 2 pi on 3 times CA. Because remember, AB is the same vector as this blue one I've drawn in. And I could get it by rotating anti-clockwise 2 pi on 3. So multiplying by the cis of 2 pi on 3. But the cis of 2 pi on 3, of course, was what they told me. Let's go back to it just to confirm. There it is. That's what they told me W was. So W times A minus C is B minus A, head minus tail on each of those vectors. Expand out, and there's my expression. Not quite what we're looking for yet. Play around with it. So I'll group the A's together, and the B's and the C's together, because I want to end up with something A plus something B plus something C. I've got the BW, I've got the CW squared, minus W squared. Aha! But now I can use that fact that they told me, remember, to end up being a cube root of unity, but they also told me this. 1 plus W squared is equal to 0, therefore minus W squared, when we play around with it, must equal 1. I have our result, A plus BW plus CW squared. Okay, now part 3. It can be shown if it was the other triangle, if they'd gone around clockwise, you get a similar result, not quite the same, and then they made sure to point out, don't prove it. I mean, it would be a very similar proof to what we just did in the other one, but don't waste time. They're saying, look, this would be the other result if you went with the other triangle. But now, if ABC is an equilateral triangle, so it could be either of those two cases, then this result holds. A squared plus B squared plus C squared is AB plus BC plus CA. We proved the first one, they gave us the second one. How am I going to get from those two equations to that? Well, if I multiply them together, I'm still going to get 0, because they're both equal to 0. Expand the whole thing out. Yes, it's a long expansion, but let's play with it. Remember, we're playing with the cube roots of unity, so things we know W cubed is equal to 1, and we know 1 plus W squared is equal to 0. Whew. Well, let me group the things that I want. I put it in the same order as what I'm trying to prove. So I've got all the A squareds over here. In fact, there was only one. B squared had a W cubed with it. C squared had a W cubed with it. Then on the other side, I've moved all the ABs and BCs and CAs are over there and grouped those together. Okay, well, the w cubes are nice. We know they're equal to 1. So the left-hand side drops out straight away. On the right-hand side, I've got a w squared plus w plus w squared. That's nice, it's a common factor. But hang on a sec, w squared plus w to the 4 is also w plus w squared because omega cubed is equal to 1. That all drops out beautifully. It's got a common factor. Now, it's close. I have to now show that this w squared plus w, I want that to equal -1, don't I? Well, it does, because again, it comes back to 1 plus w squared is equal to 0. So the negative w squared plus w is 1. Whew, we're there. We got the result. A lot of algebraic manipulation there to get there. Okay. 13e, using our Euler's formula to have some fun.